Hello everyone, a very warm welcome to this science class for class 10 students of CBSE board. Chapter we are going to cover the human eye and the colorful world. This is the 11th chapter of your NCERT book. This chapter we will be covering in our lecture series in 4 parts. The first lecture, that is your 11.1, we will discuss about the functioning of a lens in a human eye. Okay, so this chapter is basically about your ability to see the world around you, which is very colorful. So we're gonna understand why this world is so colorful and how you can see so many different uh, phenomena around you, what enables you, right? So we're all gonna discuss in this lecture. After that, you have a lecture in which we will discuss about the defects of vision human beings have, the eyes have, and how to correct them, right? And what are the applications of the spherical mirrors and lenses that you have learned in last chapter, that is chapter 10. Okay, in third lecture we will talk about refraction of light through a prism, how the light is refracted when it passes through a prism. After that we will talk about the dispersion of light, in which we will talk how a white light gets bifurcated into its constituent colors. Okay. In the last lecture of this series, for this chapter, we will talk about atmospheric refraction. Then we will talk about scattering of light, what it is, and the application of all the phenomena in our daily life. There are so many phenomena around you which are based on atmospheric refraction and the scattering of light. Okay, so let's begin. So this is your lecture 4th for this chapter. In this, we're gonna start with atmospheric refraction. Atmospheric refraction, by its name, you can define it. It's a refraction of light by the Earth's atmosphere, right? So there are so many phenomena based on this atmospheric refraction. The one that's very famous and very common observations, and even you'd have observed it, around a hot body or around a fire, you would have seen a wavering or the flickering of the objects behind it, right? We're going to discuss about it. Then there is a twinkling of the stars. From the nursery, you would have heard Twinkling of the Stars. There is a poem, right? You would, from the beginning, you have heard that. That's called a Twinkle Twinkle Little Star, right? So you know about the twinkling from very beginning. So we're gonna understand why that little star twinkles. Okay, so we're gonna understand the science behind it. Then the third is the uh, advanced sunrise and the delayed sunset. What it is your sun actually visible to you 2 minutes before its actual sunrise, and it sets 2 minutes later, right? Why it happens, we're going to discuss that also. So all these three are examples of atmospheric refraction. Okay, so we're going to discuss about our first example, that is the apparent wavering or the flickering of objects. So all of you might have observed that there is an apparent random wavering or the flickering of objects, as you can see in this, uh, through a turbulent stream of hot air around a hot body, or you can say fire, right? As it is very much visible from the figure given, right? So what is actually happening? Let's observe it. Okay, so what happens when the air around the fire becomes hotter? Okay, obviously there is fire, so air around it also become hot compared to the air farther from it. So what happens, the as the air gets hotter, it become less dense. If it become less dense than the cooler air, its refractive index slightly changes. Now you know, if there is a different refractive index, then the light ray will be deflected at different angle, refraction angle will be different, right? So that happens again, that hot air is lighter, less denser, so it tries to move upward. As it goes up, the cooler air try to fill in the gap. So what happens, there is an you can say physical condition of the refractive medium is also not stationary. So the apparent position of the objects behind the hot air seen through the hot air fluctuates. This wavering is an effect of atmospheric refraction. I hope this is very clear. What is happening basically? The air around the fire gets hotter, become less dense, refractive index changes compared to the cooler air, and because it gets hotter, it starts moving. If the physical conditions are also changing, so refractive index is also continuously changing. So as the light from the object behind the fire is coming, it gets refracted randomly. So it looks like the object behind is fluctuating. I hope this concept is clear. Let's look at another example of atmospheric refraction. That is your twinkling of stars. Twinkling of the star is also due to the atmospheric refraction of starlight. So what happens as the starlight enters the atmosphere, Earth's atmosphere, it undergoes refraction. Okay, and that refraction is also continuously happening before it reaches the surface. So as the refractive index of the air medium or the medium is gradually changing, this atmosphere, yeah, or rather you can say atmospheric air, bends the light, that is the starlight, towards the normal. Okay, so what is happening here basically? So if you draw a point, a normal at this point, and then here like this, so we can see this is continuously moving in this direction. Okay, so it starts bending. So it starts bending towards the normal, and the apparent position of the star is slightly different from its actual position. This is the actual position, and this is your apparent star position. Okay, so but interesting thing is, because the refractive index of the medium is not fixed, and why it is not fixed? Because of the physical conditions. Okay, physical conditions of the Earth's atmosphere are not stationary. That's why the refractive index is also not stationary. Okay, so because of this, there is a fluctuation of the light coming from that star. Okay, so as the star are uh, very distant, we consider them as point-sized sources of light. Okay, so as the path of rays of light coming from the star continuously changes because of the continuous change in the refractive index of the medium due to the physical conditions changing, the apparent position of the star is fluctuating, and the amount of starlight entering the eyes also changes, and it looks like it is twinkling. Okay, so we have understood here two things. First is the twinkling of the star is happening because of the changing uh, amount of light entering the eyes from the star, and the apparent position change of the star. Both of these things are happening because of the atmospheric refraction of the starlight. Okay, so this twinkling effect is because of atmospheric refraction. Now someone can ask, there are planets also in the sky, why don't they twinkle? The reason being, the planets are much closer to the Earth, okay, and are not considered as a point sized. That's why they are extended sources. Okay, so if a planet is a group of stars, or sorry, is a group of point source of light, the total variation in the amount of light entering our eye from all the individual point size sources will average to 0. That means if one is you can say twinkling, you can say its intensity is reducing 1 point, other will brighten up. So overall effect of the twinkling gets nullified. Okay, so you can say this, due to this, the twinkling effect is not visible for the planets. It's only for the stars. Okay, let's look at another example of atmospheric refraction. That is your advanced sunrise and delayed sunset. Okay, so let's look at what is happening. Basically, advanced sunrise and delayed sunset are happening because of atmospheric refraction. What does it mean? It means that sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset. When I say actual sunrise, I mean the actual crossing of the sun above the horizon. Means this is your horizon. Okay, as when the sun crosses this horizon, we say it's an actual sunrise. Okay, so because of atmospheric refraction, you are able to see the sun before the actual sunrise. Okay, that we say it's an advanced sunrise. And you can see sun 2 minutes after actual sunset. That means you can see it for 2 minutes extra. So we say it delayed sunset. Okay, so this is with respect to horizon, all the measurements. This time difference is about 2 minutes. Okay, it's very simple to understand why it is happening due to atmospheric refraction. You can see from the diagram, the rays are coming straight, but as they reaches the atmosphere, it starts bending. Okay, as they bends and reaches to your eye, if you extend them backwards straight, you will see the sun here. Actually, sun is at this point, but you will be able to see it here because of this bending of light, or you can say atmospheric refraction. Okay, also the sun, or you can say sun's disk, looks flattened at sunrise and sunset. It looks a little flattening. Okay, and that is also due to the same phenomenon. I hope this you are understood what advanced sunrise and delayed sunset is. Okay, next topic that we're gonna learn is a scattering of light. What does the scattering of light means? Scattering is a very common English word which means to scatter, to spread, right? So let's understand what does the scattering of light means. So definition is when light passes from one medium to another medium, let's say air, glass or water, then small part of light, or you can say a part of light, is absorbed by the particle of the medium. Okay, so what happens, let's say there are two mediums. Okay, so as it passes, light passes from here to this point, and mind this, when I say it's a light. Okay, so a part of the light is absorbed by the particles of the medium. There are particles, some part of this light, it gets absorbed. After absorbing, they release the radiation in a different frequency of wavelength. Okay, and also in a particular direction. So what is happening, a part of the light is absorbed by the particles. After that, they release the radiation. So subsequent radiation is released in a particular direction. So this is your scattering of light. The medium particles absorb the light and then release the radiation in a particular direction. This is your scattering of light. Okay, it's pretty simple, but we will look into the application of this. And scattering of light, uh, Tyndall effect is based on the scattering of light. Okay, next we're gonna look into what is Tyndall effect. Okay, Tyndall effect. Tyndall effect is scattering of light by particles in a colloid or in a very fine suspension. Okay, I hope you guys know what is a colloidal solution or a fine suspension. Okay, in true solution, you are not able to see the solute in the solvent, but in a colloidal solution, there are particles suspended. Okay, so there are particles which are spread across the solvent to make it, which is called a colloidal solution. Okay, so as the light passes from this, scattering of light is by the particles is very much there. This is called Tyndall effect. We will understand this effect with an animation in the next slide. Okay, let's understand the Tyndall effect from the from an animation. Okay, so what we are doing here, from let's do an experiment. What we are doing, we have a light source and we have two water glasses in the path of the light. So light is passing through the solution in air and just hitting the screen, and you can see the light image on the screen. Okay, now what is happening? What we will do, we will make one solution a colloidal solution, and we will see what happens to the light. Okay, so let's make this animated. So can you see here that this light, it's passing, this is actually the path of it, but here it is not visible. In this reason it's not visible, but here you can see the path of the light. That is because it is a colloidal solution, and in colloidal solution there is a Tyndall effect. What is a Tyndall effect? Is a scattering of the light by the particles of your solution. Okay, now this scattering of light, what amount of light will be scattered, and what color of the scattering light will be, depends on some factors. One factor is the you can say scattering particles. One factor is the scattering particles. मतलब if there is a colloidal solution, तो आपके solute जो है उस पे आपका depend करेगा कि कौन सी जो color है scattering light का वो क्या है. Okay, or if we are using white light. Okay, so very fine particles जो होते हैं वो क्या करते हैं, ब्लू लाइट को स्कैटर करते हैं. और अगर पार्टिकल्स का साइज बड़ा है, it can also scatter light of longer wavelength, like you can say around the red region. Okay, so if the size of the scattering particles is long enough, it can scatter all the lights. That's why in that case the scattered light will appear white. Okay, so this is called the Tyndall effect. Okay, so I hope this helps you to understand what is a Tyndall effect. Okay, next we will look into why the sky is blue. Okay, why do we see the sky as blue? What is the uh, science behind the bluish sky? Okay, let's understand the scattering of sunlight by the fine air particles, because of which we see the air sky as blue. Okay, so you need to pay attention what is happening here. So you know the molecules of the air and other fine particles have a very small size compared to the wavelength of the visible light. They are very small. Okay, so that's why, because they are smaller, they are more effective in scattering the light of shorter wavelength. As we have discussed, that white light is made of 7 colors, 7 consecuting color lights. So all the color have different wavelength. The shortest is the blue light. Okay, so it's these air particles are more effective in scattering the blue light compared to the red light. Red light has a wavelength of around 1.8 times greater than the blue light. Okay, so as the sunlight passes through the atmosphere, the fine particles in the air scatters the blue color more strongly. Okay, so what happens once they are scattered up? Now you can see in the previous example also you saw that scattered light goes into your eyes. Okay, so if the blue light is scattered, so that scattered light enters your eyes and you see the sky as blue. Okay, but interestingly, if you have traveled by the flight in the night, or even in the daylight also at higher altitudes, you could have seen that the sky is little darker, because at high altitudes the scattering is not that prominent. Okay, so this is also the reason that we have red color for the danger, because red color is scattered less, so it can travel longer distances without getting scattered in the path. That's why a red light is visible from a longer distances also. Okay, and it is also less scattered by the fog or smoke in the path. Okay, so that was about why the sky is blue. I hope you understand this thing. Next, we're gonna look into why the color of the sun at sunrise and sunset is different, or it's little reddish. Okay, let's look at it in the next. Okay, so I told you that we need to learn, we're gonna understand how the color of the sun changes at sunrise and sunset. To better understand this, let's do a activity. Let's see that how the scattering of light happens in a colloidal solution. I just showed you an animation. Let's look at it from an activity. Okay, so what are we doing here is we have a source of light. It's a very strong source of white light, and we have a converging lens. So, and we have put this source of light at the focus of this lens. So, if the rays are coming like this, they become parallel after the lens. Okay, so we have a parallel beam of light. We pass this through a transparent glass tank which has water in it. Okay, so this allows a beam of light to pass through, and as they pass through the water, we have a screen through which we have a small opening, or you can say a circular hole. So what happens as the parallel rays pass through it, we have another lens to converge them. Okay, so we have another lens L2 which is conversing it on the screen MN. Okay, so it is converging at this point. So this is the basic setup. Now what we are going to do is we're gonna mix 200 gram of sodium thiosulfate in the water. क्या कर रहे हैं हम लोग? Sodium thiosulfate 200 grams we are mixing. Okay, now once it is mixed, we're gonna add another thing, that is your concentrated sulfuric acid. We will put in sulfuric acid, not much, but we're gonna mix it 1 to 2 ml. Okay, so this 200 gram we mixed in 2 liters of water, clean water, and then we put in the sulfuric acid. How much? 1 to 2 ml in it. You're gonna see something very interesting. Okay, so you will be able to see that these particles of the sulfur starts precipitating quickly, 1 or 2 minutes. Okay, so slowly you will be able to see the blue light. You will be able to see the blue light through the tank. Okay, or you can say this jar in which the water is there. This is happening because of the sulfur particles, the size of the sulfur particles. They are very small, so they scatter the shorter wavelength. Okay, and the color of the transmitted light from the this side, you can see the color of it will is also changing. Okay, uh, this color initially was your orange red. Okay, and then it slowly changes to red color. Okay, so this light changes into red color from the orange red because of this blue part of it have been scattered, so only remaining part of the light reaches the screen MN. Okay, so this is the scattering of light in a colloidal solution. Okay, so scatter जो the light which is getting scattered, that is visible to you. That's why if you're seeing some blue color like the sky is blue, this is because the blue part of the white light gets scattered and enters your eye to make the sky visibly blue. Okay. Okay, let's understand the color of the sun at sunrise and sunset now. So the story is uh, the path of the sun which is nearly over the head. Okay, which is nearly over the head. So the path is comparatively shorter. Okay, so if it is shorter, it is the blue light scattered is very less. Okay, and if the blue light is scattered less, so the light reaching down is almost white. So you see the sun as normal color, the way you see that. Okay, so for most of the time it is like this. But when the sun is at the horizon, when the sun is at the horizon, the light has to travel more distance through the atmosphere. You can see here for the first case when it was overhead, the path it traveled through the path it traveled through the surface atmosphere was only this much. But after when it is near the horizon, the path traveled is this much. Because of this, the uh, scattering of the blue part is very high and only reddish part is remaining. So the sun appears reddish because of the scattering of the blue light when the sun is near the horizon. Okay, that's why sun looks at sunrise and sunset little reddish in color. Okay, I hope this you understand what is happening here. Because of the larger distance of the light has to travel, it blue part gets scattered. Okay, so that's it in this lecture. So there's a whole lecture series that you can follow, and after this we will be starting new chapter. And don't forget to subscribe this channel for more lectures on the science class for class 10th, 11th and 12th. Okay, thank you very much for your time and have a good time. Thank you.